Thanks. Well, I have been involved in this space now for 5 to 6 years at the San Onofre nuclear plant. You know, as a resident, I just started asking questions about how safe or dangerous is this, and really started looking into it. All of that led to becoming involved with a congressional representative who was running partly on the platform, Mike Levin, who was an environmental scientist. And I asked him, what are you going to do if you win? He said, I want to start a task force to really study this and make recommendations to Congress. He asked me if I'd be on it. I said, yes, I'd love to be. So we actually created then a recommendation for Congress with a bunch of recommendations. And leading that task force was the gentleman I'm going to introduce you to talk about myth busting in the nuclear space. Greg Jaczko is the head of that technical head of that task force. And he's a former nuclear regulator from the NRC, has a tremendous amount of experience and knowledge in this space. So, it's my pleasure to introduce Greg and have him talk to you about some of the myths that are out there and what's real and what's not. Thank you, Greg.
Well, thank you, Dave. I appreciate it. I have some handy notes on my phone just to make sure I cover everything. Well, it's a real honor to be here, and I appreciate Steve for inviting me and giving me the chance, and for the Samuel Lawrence Foundation that Dave has also been involved with, which is a nonprofit in Southern California that has worked on the issues, and also I believe Steve was involved with dealing with the San Onofre nuclear power plant. So I spent a lot of my professional career dealing with nuclear power and have seen a lot of things about it. Some I think are true, some are not. And so what I'll talk about today is really the biggest issue right now, which is why are we talking about nuclear power and what are the realities of nuclear power today? So there's two primary reasons why we're talking about nuclear power today. The first is the pressing need to deal with climate change. And one of the key contributors to carbon dioxide emissions comes from the electric power sector. So the traditional fossil fuel plants, coal, natural gas, that have for a long time been the bulk of the way that we generate electricity. So nuclear power, unlike those types of fossil fuel facilities, produces electricity without carbon dioxide emissions or without direct carbon dioxide emissions. So it's very attractive with the current concerns we have, or still, I believe, will have about carbon-free electricity in the power sector. So nuclear power is about a little less than 20% of the electricity production in this country. So to make a meaningful contribution to reducing carbon emissions in the electricity sector, we both have to maintain all of those reactors as well as ultimately build new ones. And that's where I think there are some challenges that I'll talk about. The other major driver really around nuclear power right now is that we're entering a period potentially where we will have significant growth in the demand for electricity, largely driven by data centers and AI applications. So for the first time in a long time, we are really looking at projections for significant demand growth, and again, driven largely by those data centers. So the idea of having nuclear power plants as a way to meet both of those challenges is very attractive in many ways. But let me talk a little bit about what some of the challenges are with those. Well, first of all, we actually have a lot of sites in this country already that have been licensed to build and operate nuclear power plants. So this gets to one of the biggest issues that I often hear about nuclear power, is that it's being stymied by regulations and overly burdensome regulations. I think, in fact, as a former regulator, I would say it's the opposite. It's really, the regulatory system has done a really good job of making sure that nuclear power can operate in this country and operate with a degree of trust. There's several nuclear power plant sites in Texas, for instance. But when I look at that fact that we have licensed reactors already, or licensed sites in this country to build new reactors, and plants aren't getting built at those sites, it tells me that there's a disconnect. The problem there isn't the regulatory process, because that's already been achieved and dealt with. The reality is that nuclear power plants today are extremely expensive to build. They take a very long time from planning to development and to operation and construction. So the real fundamental challenge that the industry is having to deal with is that problem of construction and cost. So while I was chairman of the Nuclear Regulatory Commission, we licensed the first new reactors in decades, really. 2 of those reactors were actually built. They were built in Georgia. and they were built at an exorbitant cost, several billion, tens of billions of dollars over budget. So the fundamental problem in that regulatory space isn't really there. It really comes down to more of an issue of cost. The other, one of the other issues that we always have to deal with, and this is perhaps not so much of a myth as it is just a reality, is the question of waste. Anything we do, whether it's plastics, whether it's all, as Ravi talked about, I'm a big proponent of the outdoors, and I buy all kinds of fleece and gear like that, and then I realize that all of that produces microplastics, which we're trying to figure out if that is in fact harmful or not. So everything we do creates waste. Electricity production creates waste. Nuclear power also creates waste, and that is definitely a challenge, and it's something that the industry has been struggling with for a long time to deal with. And right now, we don't have, and not just we, but really almost no country in the world that has a nuclear power program has developed a solution or a way to manage and deal with the waste. And it is a waste that, unlike other waste products, needs to be managed for many, many millennia. So it's a problem that is beyond the scope, really, of most of our institutions and our ability, really, to contemplate a way to solve these problems. So, for instance, right now, it's the responsibility of the federal government in the United States to identify and build a nuclear waste storage facility. That part of the plan that the federal government went through in dealing with that was they had to come up with a way to develop signs so that generations into the future might know and understand what this facility is that holds all this spent nuclear waste. So they had a study, and a contract was awarded, and a contest was held to come up with a sign that you could potentially put out around this site so that future generations who saw it would know and understand that it was a hazard. So it just gives you a sense of the scope of the challenge when we're talking about isolating and maintaining this material for such a long period of time. So waste will be a challenge. Is it the worst and the most significant challenge? Probably not, but it is nonetheless a challenge that has to be dealt with if nuclear power is going to succeed. One of the other issues that I hear quite a bit about nuclear power is it's the fastest way for us to deploy clean energy and clean power. And in fact, history has shown that with the exception of a very few isolated periods in which we built reactors, a lot of reactors in a very short period of time, that has largely not been the case. And let me give you some examples. So the state of Texas is a very, very good example. So in Texas in 2021, there was a very significant electricity shortage because of a very cold spell. And as a result, the electricity market in Texas, which is a unique electricity market because it's one of the only ones in the United States that's completely isolated to the state. In any other parts of the United States, electricity can be sold and moved around in large geographic regions. So there's a western part of the electricity grid and an eastern part. Texas is isolated and by itself, which is very Texas in many ways. And they did that because they're not connected to any other power grid, so it means that they don't fall under the auspices of the Federal Energy Regulatory Commission, which regulates a lot of electricity pricing and policies. Well, so it's a very good market for how the market can respond when you have something like the polar vortex, where there was challenges with the ability to produce reliable electricity when it was needed. One of the amazing things that's happened is after that, there was a boom in construction and new generation. Now, I'm not sure if you can imagine where that came from, but in fact, it came from solar. So if you look at the year 2020, in the state of Texas, about 8,000 gigawatt hours of electricity was produced by solar power. So compare that to the nuclear power plants in this state, which are about 40,000 gigawatt hours of electricity. It doesn't matter how big that is, but that's about 2 nuclear power plant sites in this state. Solar went in the course of 4 years to now providing about 48, and it's growing dramatically, 48,000 gigawatt hours of electricity. So in a short span of 4 years, the state of Texas built enough solar power to produce electricity that is now more than the output of the nuclear power reactors in this state. And China is another country to look at where you can see similar kinds of rapid, almost exponential growth in the output of renewables, solar and wind and others. So wind was always a dominant or a relatively prominent electricity source in Texas, but is that growth in solar that has been tremendous here in Texas. And again, a lot of that was a response to this need to get more power online. It's also then driven by AI demand, and is a place where a lot of data centers want to come because they can get access to solar power. Now, the advantage of that resource, for instance, is that it's relatively cheap and relatively easy to deploy. But you need to couple it often with battery storage and other technologies so that you can match when the electricity is produced by the solar with when it's actually needed by the population. So, you know, there's a lot of information out there that says that nuclear is in fact this technology that can deploy quickly. That's largely statistics that are skewed by the construction in a few countries of a large number of power plants in a short period of time and those reactors coming online. But what we see in the world today is exactly the opposite, that countries that are developing clean energy quickly are doing it with wind and solar, and to a very large extent solar. And as I said, China, which is often one of the countries that is talked about as one of the dominant sources of nuclear power production, is actually building 8 to 10 times more solar today than what they plan to do in nuclear over the next 10 to 20 years. So in terms of technologies that really can grow rapidly, we have those technologies today, and it's not nuclear power. Now, one of the other issues that I see a lot, this is often in the media, every time you'll see some AI company or another technology company will sign some agreement to build new reactors as part of an AI or data center. For instance, a good one is Google had announced an agreement with a company called Keros to build nuclear power plants to power data centers. Switch, which is a large technology data center provider, announced a deal to build 12 gigawatts of nuclear power with a company called Oklo, which is also has a presence here in Texas. And I look at that, and then I go back to my roots as a regulator, and I say, well, what is actually happening on the ground? Because the regulator is going to have to process that and deal with it. And in fact, for both of those companies, there's very little that's happening. Right now, there are 2 reactor sites that have permits that are pursuing reactors in this country. One is actually also here in Texas with a company called X Energy, which is also based here in Texas. They are going through a process of acquiring what's called a construction permit, which is the right to be able to begin construction of a reactor. And there's a plant that's being built in the Northwest, TerraPower, which is a Bill Gates-backed company. Both of those plants are following an older model for nuclear power plant licensing and construction that will likely take at least 5 to 7 years for the first plant to be built. So, you know, we're talking early 2030s until we could realistically see some of those plants. But when I read the press releases and I read the news stories, what I see is plants will come online in I think one says 2027, one says 2028. Those statistics are simply not real. These plants will not, if they're lucky, even get through the licensing process by that time. And of course, that brings me then back to my first point, which is the licensing process and the regulatory process isn't really the biggest challenge. The Nuclear Regulatory Commission is a very competent organization that knows how to review and approve applications, if those applications are sufficient and appropriate. It's like anything. If you go to take a test and the teachers tell you everything you need to study and you go and you fail your test, that's probably not the responsibility of the teachers. It falls to the student who took the test. Well, the nuclear power industry is in that mode as well. They have been told all the things they need to do, and many of them are just not ready, in particular those companies that are spending more time signing agreements with technology companies in order to plan for reactors that have yet to actually go through any kind of approval process. So if you take Oklo, for instance, they are the group that has agreed to 12 gigawatts with Switch. They have projected and said that their first reactors would be ready by 2027. That's 2 years from now, and they have not even submitted an application. So even if the NRC were to move expeditiously fast, that still leaves no time for construction. So it is a big challenge. It's an industry that I think will have will have a lot of continued challenges dealing with these issues. Now, one thing, as I said, when we look at this issue, I said at the beginning that really we're looking at technology and we're looking at climate change as solutions. Well, if, let's say, we were to take what we have today in the world, globally nuclear power provides about 9% of the electricity production. So from an electricity production standpoint, it will be very, very difficult for nuclear to become a dominant player in global electricity production or carbon-free electricity production. So at a recent convention of the parties for the UN dealing with climate change, an annual meeting that's held to talk about climate, a goal was established to triple nuclear power capacity by the year 2050. Well, even in the best case scenario, and that's capacity, so even in the best case where we don't grow our electricity demand, at best we'd be looking at 27%, but most likely it'll be much, much less. So the reality is that no matter what we do for climate change, if we are going to address climate change, it will not be driven by the nuclear sector. It will be driven by that other 80% of the electricity sector that needs to be decarbonized. So the question is, by 2050, will we, if we've figured out how to generate 60, 70, 80% of our electricity from renewables and storage, will it be easier to get the remaining 20% from nuclear power or better renewables, better storage? And in that case, I would bet that it's more likely we'll see the advancements, because when we're building out that much renewables, the economies of scale, the economies in the manufacturing sector, in technology advancements will only get better and faster than they already have. Meaning that for nuclear to kind of squeeze into that last component is going to be very, very challenging. So maybe I will stop there, and I will, I think, turn it over to Mark Jacobson. Yes, are there any questions for me? Yeah.
So building nuclear power plants in the near future is still feasible economically, or is it still going to be super expensive?
It's absent significant subsidies, it's not economical in most parts of the world. It's certainly not economical in the United States. And again, that is primarily the challenge with the technology. It's one that the industry continues to struggle with. I mean, it's never really been economically viable to build nuclear reactors. We went through a period in this country, and some of it, again, has to do with the nuances of how electricity and power plants are built and the financial systems, the utility systems. We used to operate in a world in which almost the entire country was in a rate-regulated electricity state. So if a utility built a plant, it didn't matter how much it cost. They just charged that to their customers, to the ratepayers, and they had to pay that. Ratepayers then got an adjustment in their bill, and that would happen. So in Georgia, where these 2 reactors have been built, because they went so over budget, they're seeing a substantial increase in their rates there. So in that system, in a way, it didn't really matter how much it cost, because you built it, the utility decides to build it, you have to pay for it. Now we operate in a world where there's more competitive pricing electricity, and in those cases, it's very, very difficult to build nuclear reactors. Again, Texas is a great example. There is a power plant site in Texas at the South Texas Project, and in the late 2010s, when I chaired the NRC, they had plans to build a nuclear reactor or build additional nuclear reactors at that site. Those sites actually went through the licensing process, but they were never built because it was cost prohibitive. Because Texas operates more like a commercial marketplace in which you have to have a business plan and you have to be able to recoup the cost of your capital expenditures, and the price of power is simply not enough to recoup that when you could build all of these other things like solar and wind far more cheaply. So.
We're going to go ahead and move to our next speaker, just given the time gap. But I got to tell you, first of all, thank you so much. Give him a round of applause for Greg. For those of you that are here that have been fortunate enough, frankly, to have been here and listened to this, I got to tell you, you just heard some very valuable information from a very knowledgeable source. And I forgot to mention also that Greg is teaching at Princeton and has a book you may want to get called Confessions of a Former Nuclear Regulator. but he'll be around probably. We're going to go through a little bit of our break period coming up. We've got one coming up in about 8 minutes or so. We're going to have our guest who got hung up in the air, not his fault, but was able to make it here to give us some more really good information on this. So again, thanks so much.
Sure.
Yeah, really appreciate it.
Thank you.
Thanks. Mark, come on up. So now my pleasure to introduce somebody from the other coast, Stanford University, Mark Jacobson. Mark is a renowned leader in the climate space, an amazing researcher, has tremendous knowledge and influence in the space, and has written a terrific book called No Miracles Needed. Would encourage everybody to get that. I happen to have both these books. And so again, really delighted to be able to introduce Mark here. But I'm going to let Mark go ahead and address issues from his perspective as well on myths. And then if we can, definitely get a question or two down. And as I said, no worries about running into the break a bit. If you need to grab some coffee, please do. Anyway, thanks, Mark.
Thanks so much. So I work on renewable energy, but also looking at all energy sources in terms of their ability to address air pollution, global warming, and energy insecurity. And so I've looked at nuclear quite a bit over the last, since original study was back in 2008 or so. So the main issues I want to point out, and maybe it might be overlap with what Greg talked about, but I'm not sure exactly what he said because I wasn't here. But there are 7 issues that I want to point out. 2 are related to cost and delays, but the other are based on energy insecurity issues. So the most obvious is the long time lag between planning and operation of a new nuclear power plant. And this will apply to small modular reactors as well, which right now don't exist on any commercial scale. It used to be 10 to 19 years. There's no reactor ever built in history that took less than 10 years between planning and operation. And that's different. Most people look at just construction time, and you can find construction times that are 4 years or 5 years, but not planning to operation times. That's the time to not only plan a site or locate a site, but also to get permitting, to get financing, to actually all the process before you actually start construction. And so it used to be 10 to 19 years, but now in the last 5 or 6 years, it's actually increased to about 12 to 23 years is the planning to operation time of new nuclear. The Vogtle plants in Georgia, the 2 reactors, each took 18 and 19 years respectively from planning to operation. And France, Flamanville, France just became operational after 20 years. That's their first reactor. Vogtle, by the way, those 2 reactors are the first reactors in the United States to start from scratch in the last 30 years. And in UK, there's the Hinkley plant that's going to take at least 23 years between planning and operation. In Finland, there's a plant that just opened last year, and that took 23 years. There are in the UAE, there are 4 reactors, the Baraka reactors, that took 12, 13, 14, and 15 years. So those are on the lower end. That's where you get the lowest end. And even in China, which is growing more nuclear than anybody else, it's also 12 to 17 years from planning to operation. But just to put in perspective, China last year, they put in 3.9 gigawatts of new nuclear, but they put in 370 gigawatts of new wind and solar. So almost 100 times more nameplate capacity of wind and solar than nuclear. And worldwide, there's less nuclear output last year than there was in 2005. So whatever's being built more of it's being retired than being built on a worldwide scale. So there's no growth in nuclear, and so it's kind of surprising that you'll see all this push for new nuclear reactors when it's just not being built. It takes so long. And then let's look at the cost of the nuclear, which I'm sure Greg talked about to some degree, but the Vogtle reactors cost $35 billion, and that's equivalent to $16 a watt almost. which for comparison, new solar is 80 cents a watt. So that's 20 times the capital cost of new solar is the new nuclear reactors. And that's the same cost in from several other reactors are also about 20 times new solar, but there are some that are down to 10 times. So it's somewhere between 10 and 20 times the capital cost of new solar, and also wind. Wind is also similarly cheap. But if we look at the cost per unit energy, which is what most people want to look at instead, it's still 3 to 8 times the cost per unit energy than new solar or new wind. And so in terms of costs, in terms of delays, it's, why would you want to wait? Well, a new wind farm or new solar farm, it takes anywhere from 1 to 5 years from planning to operation. Rooftop solar, you can do it in 6 months. So why would you want to wait, up to 18 years longer, or, even if it's 11 years, it's still too much. 11 years longer to 18 years longer, or 22 years longer in the worst case, for something that costs 3 to 8 times more per unit energy. We only have 5 years to solve 80% of the climate and pollution problems we face, and another 5 years after that to solve 100%. And so if we delay, if we try to pick a technology that can't even be built within 12 years when we need to solve 100% of the problem in 10 years, it's just not helpful at solving any problems. So those are the kind of economic and delay reasons. But the other reasons, which some people gloss over, but other people find really important, meltdown risk. Of course, 1.5% of all nuclear reactors ever built have melted down to some degree. There's, of course, the nuclear waste issues. You have to store the waste for hundreds of thousands of years. There's the nuclear weapons proliferation risk. There are 5 countries, at least in the world, that have developed nuclear weapons secretly under the guise of civilian nuclear energy programs or research reactor programs. There is carbon emissions. Nuclear is not carbon-free despite all the claims. It's not even close to carbon-free. It's 9 to 37 times the carbon equivalent emissions as wind. Half of that's due to the fact that while you're waiting around, the extra time, all those, the extra up to 22 years, but let's say it's 10 years to 22 years, compared with wind or solar, you're running the background electric power grid, which runs on fossil fuels. So you have to count that. Those are called opportunity cost emissions. Opportunity cost emissions are those emissions that running from the background grid while you're waiting for the nuclear reactor to be built. But you're not only getting emissions from the background grid, you're also getting a lot of emissions from the production of the plant. Like the Vogtle plants, they put in enough cement in to lay a sidewalk from Miami to Seattle. And all that cement puts in a huge amount of CO2, carbon dioxide, that doesn't get recouped for decades afterwards. And so there's construction emissions, there's planning to operation delay emissions, but there's also, you have this mining and refining of uranium, which is continuous over the life of the nuclear reactor, and that's a very energy intensive process that results in emissions. But then there's emissions people never count, which is actually occur, which are water vapor emissions from the steam from cooling water, and also the direct heat emissions from the nuclear reactor. So it's not a large amount of emissions in terms of carbon equivalent emissions, but you have direct heat and you have water vapor, which is a greenhouse gas, and that results in a few grams of CO2 per kilowatt hour, grams of CO2 equivalent per kilowatt hour of energy. But when you add it all up, it's 9 to 37 times the emissions of wind. So it's not carbon-free. It's not even close. And then there's the final issue is the underground uranium mining risk. Half of uranium is from underground and half is overground, and there's a significant lung cancer risk because when you get uranium, you have radon. Radon decays to polonium, and polonium is a carcinogen. Well, there's other products that get into particles that people breathe in, that miners breathe in, and so there's been a historic link between uranium mining and lung cancer. So anyway, we don't need new nuclear, because we have plenty of clean renewable energy available, and there are 12 countries of the world that are running on virtually 100% wind, water, solar alone, most of them dominated by hydro. But we can even look at U.S. states. In 2024, South Dakota provided 118% of the electricity it consumed with just wind, water, and solar. 80% wind, 35% hydro, and about 3% solar. It also produced some gas and coal, but it produced over 138% of the total electricity that it needed and exported the difference. But the point is, it produced 118% of its electricity from just wind, water, solar. California is today is the 40th day in a row that California has been over 100% renewables on its main grid. And I don't know if you read the, yeah, thank you. That's cool. And you might, well, another interesting thing in California that yesterday was announced that California is now the 4th largest economy in the world. It just passed Japan. But what I think is more significant about that is that its grid has been 100% renewable now, not only 40 days in a row, but 82 days out of the entire year 2025. That's like out of 112 days or so. And that's way more than last year. And it's running on average over 50% renewables every hour of the year on average, now 51%, which is 5% better than last year, which is 5% better than the year before. And in fact, gas is down compared with last year, 26%, compared with 2 years ago, 45%. So in 2 years, we've dropped 45% of the gas use in California, which is amazing. Yeah, so that's really significant. And but it's because of the growth of solar, growth of batteries. Batteries have tripled in 2 years in California. So my point is, it's supposed to be about nuclear, but we do have a nuclear reactor still active in California, Diablo Canyon. It's providing about 2 gigawatts out of an average of 24 gigawatts, so it's a small amount, but it's not needed. It's not needed because there's so much growth of renewables. What's happening is we have, like yesterday, there was almost 10 hours straight of over 100% renewables. It reached 156% renewables on the grid around noon. And so the excess is going to batteries and then also exported to out of state. And those batteries are then going to nighttime. On Monday, it was another record. There was 1.1 more gigawatts of batteries were added on the grid in one day. And that brought it to 9.75 gigawatts of batteries on the California grid. The average demand is 24 gigawatts. So you can do the math. That's a huge growth of batteries. And those batteries, plus solar, plus the wind, plus there's geothermal and the hydro, all in combination allow the state to be almost 100% renewable. Well, 100% renewable for part of the day, every day almost now. And the point is, you can just see that all you need to do is grow solar, wind, batteries, and also now there's enhanced geothermal, which is base load, and you can replace that flat base load from nuclear with that. In fact, California is bringing in 330 megawatts of enhanced geothermal from Utah, and that's now becoming cost competitive and it's commercial. So maybe I just want to leave some time for questions. So, because I think I have 2 minutes left, but yeah, does anybody have any questions? Yes.
Thank you so much for your talk. Thank you for being here. I just wanted to know, it's a little bit more of a personal question, but how is it that you came into this role of monitoring all of this all the time and being somebody that speaks to the solutions that are available now? And how is it that you kind of found the bravery to take on folks who have been, attacking renewables and then have attacked you personally because you are smarter than them and they get annoyed about it? How did you kind of find yourself in that role?
Well, I mean, I started my career because when I was a teenager, when I was 13 years old, I would travel to San Diego and Los Angeles, and I saw this horrible air pollution that people had to breathe in. And I said, why should people live like this? And so I decided that's what I wanted to do, is to understand and solve that air pollution problem when I was really young, but I couldn't do it obviously at that point. So I focused my studies and my career on trying to understand and solve large-scale air pollution and ultimately climate problems as well. And when you think about solving these problems together, climate and air pollution, but also energy security was thrown in there a little bit later, then your solution set is different from when you're just looking at climate, for example. Because to solve pollution, you need to get rid of combustion, essentially, because most pollutants that cause health problems are from combustion. And also happens to be the most greenhouse gases that affect climate, and also particles that affect climate are from combustion as well. So you really need to eliminate all emissions. And so so if you really look carefully at the subset of technologies that are available to solve all these problems simultaneously, you really have to narrow them down and eliminate a lot of technologies. And even if you think nuclear is clean, which a lot of people think it's clean, it's just the problem is you can't. There's energy insecurity. If you're not interested in energy security, then yeah, you'd include it. If you're not interested in a fast solution, you would include it, or a cost-effective solution. So even if you think it's clean, it has so many other problems associated with it. That's why it's excluded. So I look at things kind of from a purist point of view. How can we solve these problems most efficiently and quickly to have the most benefit? If you think, because 7.5 million people die of air pollution every year right now, and so we need solutions that eliminate all these emissions in a year, today. So we can't wait 10 years, 20 years for a solution to that. And so that's really why I end up focusing on these clean renewable technologies, because they're the only ones that you can deploy on a large scale quickly. Of course, everything is subject to political willpower, and even if if it's financially feasible, you have a lot of people opposing or who just don't like things because either financial interest or just ideology. So yeah, it's just a question of focusing on what works the best for solving all these problems simultaneously.
So the second part of that question was, how did you find the bravery to go into debates, to test people who really want to try to attack you personally?
Well, that comes from, I mean, I think that's the solution is bigger than me. So it's like I have to, if I believe in the solution because that's what I work on and that's what I study, then to try to solve the problem, that's a bigger goal than worrying about my own credibility, I guess. Although I feel like I need credibility to be able to talk about it, but it's really important to. Yeah, I think it was just a more important goal to try to solve the problem than to just shield myself from any criticism.
All right. Thank you. Thank you so much.